This is StarTalk Sports Edition, a Cosmic Queries version. We're going to talk about the Winter Olympics. Ooh, yeah. And we got Gary O'Reilly.
Hey,
yeah, do they play soccer in the snow? Do they play soccer in the snow?
Yeah, we will do. It depends if it's too bad, no, because the ball doesn't roll. But yeah, we'll play frozen and in the snow.
I gotcha. And Chuck, you avoid cold weather at all cost.
Yes, it's an homage to my ancestors.
In the depths of Africa.
Yes.
There's no snow.
Yes. Yes. For all that came out of the Serengeti, I'm representing.
So this is a very broad topic because we want to talk about the Olympics in general, the Winter Olympics, the events, the fact that it's in Beijing. And, anytime we have a broad subject like this, there's only one go-to person, and that's our geek in chief, the one and only, my friend and colleague, Charles Luge. Charles, welcome back to Star Talk for the 100th time.
Thank you, Neil. It's my pleasure. Thank you. Hello, Gary.
Hey,
hello, Chuck.
Charles.
Or should I say Lord Nice?
Lord,
Oh, my God.
You were on that episode. Yeah.
Does everybody know
Charles
that
Lou
it
was
was Major General Deanna Burt that anointed Chuck Nice with this title?
With the lordship, she certainly
Yes.
did. Yeah.
And it comes in.
was a
It comes
pleasure.
in, and I always forget, and people remind me. So Charles, you are a professor of astronomy and physics at the City University of New York at Staten Island, and
Correct.
You recently become chair of the department. Is that correct?
Yes, and it's been fun. I have some great colleagues, some wonderful students, and if anybody watches The Chair, the TV show that's become popular lately, that's like 5% of maybe my regular life, but it's a lot of fun. I have a good time with it.
Okay, so I smell a reality show in the making here, where Charles Lou really shows what this is about.
Yeah, we'll
And
call
then
it the lounge chair.
Good one, Chuck. Good one.
The settee.
Chuck. And Charles, hearing from the grapevine, you've got a podcast in the making. So we all look forward to seeing that post. And
Thank you.
You told me offline that it's called the Luniverse.
Yes.
I see what you
The
did
Luniverse, yes.
Charles Lou.
I didn't come up with it. Family members around the dining room table, they were like, why don't you call it the Luniverse? I said, really? They said, yeah, sure, why not? So it should be fun. We're really looking forward to it. It should be a lot of fun with talking with fun folks. We'll have a good time.
Excellent,
Very cool.
excellent. It's a Cosmic Queries grab bag on the 2022 Olympics taking place in Beijing. So the questions are open for anybody and anything. And Gary, Chuck, who between you has the questions for us?
I think Chuck and I can share them between ourselves. Let us kick it off. Welcome to Charles, obviously. Great to have you back. Right, Michaela Nagus. These are all questions from our Patreon listeners.
I'm sorry, what you call me?
Michaela Nagus.
Oh, okay. Oh, okay.
All right.
I got nervous for a second.
All right, just working on my pronunciation here. I couldn't trip up on that one too quickly, could I? So, why does the temperature of Olympic ice need to be different for figure skating, speed skating, and hockey? Could an ingredient be added to the ice to make it more ideal for the athletes, for example, making it smoother, harder, softer, etc.?
Wow,
Yeah.
I didn't even know that. Chuck, Charles, did you know that?
Ice changes
course you
all
know.
the time.
Okay. Sorry.
Ice is Ice for sports.
First, basic fact. Are all three of those ices pure water, or have they added anything to it?
Usually, things have been added. They are often pure water, but if they are pure water, even then there's changes because they change the temperature. They freeze it at different temperatures, hot or cold. Just because something's freezing doesn't mean that it stays at that same sort of texture and temperature the whole time. This is actually used on purpose in a lot of different places. There's a famous example in ice hockey, in college hockey. depending on where you go to play your hockey, the ice is either really fast or really slow.
Yeah.
Depends on their team.
Wait, is this like the deflate gate with Tom Brady, where you can change?
Well, no, and that happens
Yes.
naturally, Neil. So, for instance, the Canadians have, Charles, back me up on this if I'm right or wrong. The Canadians have just historically hard ice, but if you go and play hockey in LA and someone's left the arena doors open for a while and that hot air comes in, it affects the quality of the ice.
It totally does. And the refrigeration underneath the ice, of course, can be strongly adjusted to any situation if you have an indoor rink, right? So what happens with indoor activity is...
Wait, Charles,
for
I just
example,
have to establish here.
Yeah.
Wait, I just have to
Sure.
establish here, because I think some people might not know this. I think you were
Okay.
hinting at it, but let me just drive it home. Water freezes at 0 degrees Celsius, 32 degrees Fahrenheit. And we call that ice, but you can have ice at any temperature below that. And the properties are different
Correct.
depending on what temperature the ice is. So ice is not ice is not ice. It depends on how
Correct.
cold the ice is. Okay, is that I think I got that right.
Yes.
Okay, now the handle.
that is exactly true.
And at what temperature does it get down to gangster rap, like Ice-T and Ice Cube?
Well, nice that you should mention that. On Titan, right, the moon of Saturn, the temperature of the ice is hundreds of degrees below 0 Fahrenheit. And so the water ice is as hard there as granite is here on this Earth. So they build mountains with it. You can see all kinds of geological features that's built with water ice that you could not do here because the moment you
Wait, what do
try
you
to
mean
do
they
that-
built the ice? You're talking about aliens
I was
on
gonna
Titan?
let that one
they
go.
built the ice.
Oh, that's an excellent point. Who is they?
They built mountains
built.
on Titan. Yeah.
But the answer, bottom
you're not
line,
allowed to
Gary, get
divulge
back to
anything more
science.
than that.
That's Yes, Gary. The temperature varies, and each rink does its own thing, and each sport has its own regulations as to what you are allowed to do in terms of temperature, in terms of additives, in terms of those sorts of things.
Yeah, the hockey players don't like soft ice because the puck doesn't move.
Some hockey players
Sweetly, yeah.
love soft ice. Think of the
Yes,
very
why?
large, bulky folks who, like the Wayne Gretzky's of the world, would zip right by.
The slow
right?
guys. The
but-
slow guys
yeah,
like the
but-
softer ice.
Yeah, and there are famous or infamous examples of really good hockey teams with fast skaters going into a visiting rink where the players are slower, and suddenly it's like they're on molasses, and you see like water
That's
spraying
Tom Brady
off their
letting
ice.
the air out of the ball.
Yeah.
That's Tom
Kind
Brady
of like
letting
that.
the air out of the ball.
Very kind of like that. Yeah.
So is it possible to get ice so hard that like a speed skater's blade wouldn't even allow it to turn? Like you would literally skid across the ice instead of skate across it.
On Earth's surface, probably not,
Okay.
but elsewhere in the universe, for sure and absolutely.
Oh, cool.
Okay, so it's all about what kind of speed that they want. So figure skating versus hockey versus speed skating, then it's pretty clear. You can put that on a chart.
You kind of can, yeah. Yeah, and remember what the skates look like, right? A hockey
Yeah.
skate is straight. The blade is straight. The figure skate's got a little divot-y thing right at the tip, so you can dig into the ice and jump up and do your spins and things like that. And if your ice is too hard, then
It doesn't
you can't
make a
dig
difference.
effectively, right? But if it's too soft, then you also can't dig very much because you got this sort of layer of soft stuff. So, yeah, people have to adjust very, very
So
carefully.
Charles, one other
Rules.
thing. Why are speed skates longer in their blade than hockey skates?
I presume that has something to do with the ability for you to push off and get higher velocities going in a straight direction, right? I mean, Gary, you're probably more an expert about in terms of the relationship between how long you can push, say, off the ground or something, and thus how much stride you can get or how much speed you can pick up, the kind of acceleration or explosiveness.
Is there a relationship to the amount of time the skate stays on the ice? And you're able to impart energy through that. So therefore, a longer skate allows you that fraction more contact with the ice, and therefore pushing energy in to get push out.
Yeah, I bet you that's true. And if you want to stop, too, a longer blade gives you more when you're at a 45 or 90 degree angle, you're able to brake faster. right? Because you have more of a surface with which to push friction against the ice.
All right, so, okay, yeah, more
Of course,
questions.
we have a very curious audience, Neil. All right, Dylan, or DeLeon, if Chuck prefers me to pronounce it like that. Hello,
Badly.
Dr. Tyson, Dr. Lou, and our great comedic co-host. Yes, of course. I love to ski and have always wondered something. This is from Dylan, of course. Snow and ice aren't exactly the same things, and we know ice has a thin layer of water, less than the width of a bacteria, he believes, which makes ice sports possible, such as skating. Does skiing also have to do with pressure melting, or is there something else going on with snow?
Wow. The answer is both are true.
Ooh.
The snow isn't even...
First explain pressure melting. Explain that.
Well, there is a relationship where if you have more pressure on water or ice, it is more likely to melt. This is untrue for most substances, but the more you push on something, more you push on ice, the more likely it is to be able to liquefy. This is a particular property of ice which is rare amongst substances here on Earth, and that allows us to be able to do these things like skate across ice with that tiny film of water, that bacteria with film water that we talk about. But it's a very complicated system.
What is the molecular transaction that's happening where pushing pressure causes melting? Because that's how they make the big ice balls for my scotch, which I never.
That is how they do it. Right?
Yeah, I never questioned it.
How you make a snowball? You take the snow, you smush it. Whoa, there's your ice ball.
Right. I never question it because I'm about to drink some scotch, so I don't care.
Well,
but what is the molecular transaction that the pushing makes the melting?
Well, we shouldn't get too deeply into the specific chemistry right now because it takes a long time to sort of make the descriptions. But basically, a water molecule is a V shape, right? It's got the oxygen in the middle and it's got two hydrogens off to the side, making kind of a V. It's a polar molecule like this. And when ice freezes, it has a tendency just to touch on the hydrogen bonds. It doesn't want to just squish in, but it wants to form a hydrogen bond lattice or a crystal. And as a result, it winds up with extra space between the molecules, space that would not have existed in its ordinary liquid form. Okay. And so that basically allows all kinds of strange things to happen. And so snow is ice water, right? It's solid water, but it's in small crystals as opposed to one big slab of solid material. So when you pack a whole lot of little things together and you create a surface, it's a different surface altogether from if you have a single slab of the same object, everything stuck together. The difference between, say, a sandstone walkway and a sandy beach. So snow gives you even more variation on, say, going across its surface than the sliding across a slab of ice. So the answer to the question here is indeed that snow variations, changes, temperature, pressure, weather, wind will make all the difference in the world when it comes to a snow sport.
But in fact, if you ski a lot on a fluffy snow slope, it eventually becomes sort of, you've melted many of the surface layers of crystals,
right,
of snowflakes, and eventually just becomes icy.
Yeah.
It's no longer fun to ski
You will
on,
start
right?
packing it down
right.
more and
Right.
more and
Start
more.
packing
But then
it
again,
down.
if you're in competition, Neil, you want to go faster. So icy, quicker, fluffy, powdery snow, slower.
Yeah, but there's a very delicate equilibrium that you have to find because if it's too icy, you can't turn. So in the giant slalom, you want a kind of nice balance between that powdery and that icy so you can grip with the edges of your ski, but yet at the same time you can achieve the turning. So you have the fast and the turning at the same time.
Chuck, you know the deal. If it's too icy, you find the nearest tree. Because you just in a straight line. Right.
Wait, Chuck, we established in a previous episode that we're not taking skiing advice from you.
We are. Yes, we are.
We're not.
We're taking
not
skiing advice from Chuck.
No skiing advice from the dude who's sitting by the fire in the lodge. Yeah, I'm sitting by the fire with some brandy, just like, you do realize the reason you weren't able to turn was because.
Before we take a break, I want to add something to what Charles said. So, because water expands when it freezes, it can only exist in that expanded state as ice. If you successfully squeeze it, it cannot be squozen as ice. The only way you can squeeze it is for it to change state and then become smaller in its volume.
Wow.
And so that's why. So you're skating on the ice, the pressure forces it to turn back into water even at the lower temperature.
Wow.
That is exactly right. And then if you're going down a ski slope or a toboggan slope, or, like a bobsled or something, remember a lot of that stuff is outdoors. So what if it starts to snow? Then you have even more stuff on there. It gets even more complicated. The weather makes all the difference in the world. I remember 1984, I think it was, the Sarajevo Winter Olympics. Billy Johnson, the American, was the first person down the mountain. And then the weather got worse and worse and worse, and all the rest of the competitors could not keep up with that first time because that first time was the ideal condition, regardless of what anything else happened with the surface, because the atmospheric conditions had changed.
Cool.
Dude. All right, we're going to take a quick break. When we come back, more Cosmic Queries grab bag on the Winter Olympics with our geek in chief, Charles Liu. We're back. Star Talk, Sports Edition. Cosmic Queries grab bag got Charles Liu, who's our go-to person anytime we're all just confused about everything.
It's always a pleasure to be here, Neil. Always fun to chat with everybody.
So we're just pulling questions out of this grab bag, and Chuck or Gary, who's got the next one?
Okay, I'll jump in. Right, Eric Varga says, "Hello, Dr. Tyson, Dr. Liu, but he's downgraded you, Chuck. You're now Sir Chuck. You've lost your lordship, apparently."
He doesn't know that Sir is less than Lord. He doesn't know
yes.
that.
Yeah, he does now.
Or maybe he's very well aware.
All right. Can you explain how Newton's 3 laws apply to the sport of curling? Are there any other laws of physics involved that play a vital role? In advance, he says thanks.
Wait. Did the word sport and the word curling show up in the same phrase?
Absolutely. Absolutely.
Don't be such a snob. Curling is a distinguished sport.
I'm mortified.
Go. Neil,
It's
curling is one of the oldest team sports in existence. Look, this show's going to come with a history lesson whether you like it or not, right?
Okay.
First invented in Scotland, and the first documented match was between a monk and an abbot in Paisley Abbey in Scotland in 1541. So the moral of this history is, when you lock people up in a monastery for a long time during winter, they come up with curling. Just saying.
Curling, the sport of sexual frustration everywhere.
So, about Newton's 3 laws of physics and anything else you can throw at curling.
Yes. Well, Newton's 3 laws, as most of us know, is that first law, right? An object in motion tends to stay in motion in a straight line unless acted upon by an outside force. So the guy pushing the stone forward, it's just going to keep going and going and going, and that's why you notice that it keeps going and going and going unless acted upon by an outside force. Okay? Now, the second law of motion, force is mass times
just to be clear,
acceleration.
it keeps going because the friction is very low. Otherwise, the friction would stop it, right?
Well,
so
you are front-running me on that point, Neil. You're absolutely
sorry.
right. No, it's good. It's good.
Okay, go ahead.
See, because you're doing exactly what scientists should be doing, right? Which is jumping in and saying, but, right? And the but is Newton's second law, which, as you know, is force is mass times acceleration.
It's also Sir Mix-a-Lot's first law.
I like big... Okay, never mind.
All right, go ahead.
What is creating the mass times acceleration, right? That's the second thing. That's what Neil is bringing up. And friction, as it turns out, will cause mass times acceleration to be exerted on the stone that's moving forward. And so the second law requires that you wind up making sure that the friction is just right. So the amount of force and acceleration that you get, the change in direction and then the change in speed, is what you want. So those guys in the broom up front, they are quickly changing the coefficient of friction of the ice on the whole time. The brushing, I've never known if exactly before every run, the curling people put like a whole bunch of snow or shaved ice on the track.
No,
ahead of time.
Charles, back in the 16th century when curling was invented, it was taken place on frozen locks and frozen ponds. So what you have now with indoor curling ice is pebbly. It's not a smooth silk finish, it's pebbly. So what the guys with the brooms are doing, they are taking away those pebbles as much as they can in a certain way. And the big clue about what this sport's all about is in the title, curling. Because a stone will curl maybe 3 times on its way to the target, or it might curl 10. But the deviation is there.
And therein lies the third law, Newton's third law of motion. When it reaches its destination in the curled direction it wants, it hits other stones. And for every action, there is an equal and opposite reaction. Mm-hmm. That's Newton's third law. So the stone hits the other stones that are in the scoring area, either knocks them out or pushes them a little bit. So Newton's laws of motion are involved in all stages of this exciting, thrilling, super fast, high energy sport called curling.
Yeah, man. Let me just say this. As a former janitor, curling is the best sport ever.
Wait, so Charles, something I never thought about.
Yeah.
So as they're brooming material into the path of the I keep thinking curling stone. They can slow it down, but they can't speed it up because it only has the speed it has at that moment. But they can also change its direction.
Yeah, absolutely.
By putting more friction on one side of it than the other.
Right.
Man.
Right. So the physics of the brooming people is extremely significant. The push, once the pusher pushes the stone off, his work is done. And all the rest of the team has to figure out where to push it forward based on the pebbliness or the shaviness of the ice.
So here's something to add to this conversation. As I think you'll understand, I don't get a chance to do this very often, but the curling stone is not flat on the base. It's actually concave, so it has a rim around it. So when it's traveling forward, the likelihood, and please disprove me, is that there's a little tilt on the front edge, which causes a little bit more friction, and then you've got an added rotation to the stone. So is that making sense to you, Charles, as I explained it?
It does in an important generalized way. We talk very glibly about ice melting and pushing and things like that, but actually the surface physics, the connections between surfaces of ice and curling or skis or anything like that is still rather poorly understood. A lot of it is still under experimentation today at the highest levels. What happens when one surface touches another? And that physics right at the edge there remains mysterious in a lot of different ways. So many hypotheses have to be put forward, and then they're either confirmed or debunked depending on the circumstances of the time. But it's a very complex question. So what you bring up is definitely an area for future study and research.
I would add that if you've ever gotten your brakes changed on your car, generally the front brakes wear out sooner than the rear brakes, because when you stop the car, the momentum of the car is carried more in the front wheels than in the back wheels. So Gary, that's my conduit to what you said. Where if it's going forward and there's any friction slowing it down at all, that front edge is going to respond to it more significantly than the rear edge.
Then again, you'll have to go from front-engined vehicles to mid-engine vehicles where there's weight distribution. But that's another conversation for another time. But I think, Charles, you've given us an
Charles,
idea.
What do you know about that? In a rear-wheel car, isn't it still the front brakes that get most of the...
It varies a lot.
Wear?
Again, if you're driving
it might change
flat,
if you just move the engine to the back.
Right. Well, it depends on if you're moving on a flat surface or whether you're climbing hills. Are you stopping a lot while you're going upward or downward? You are pushing more of your mass and force forward to the front, because a car, even though it feels like a rigid body, actually has a great deal of give to it, right? A lot of springs, a lot of flexible parts to it. So it's not a dead set thing. With our typical driving in suburbia, for example, I think, Neil, you're right on. But the complexity of driving gives us all plenty of fodder or area to be right or wrong
And
on these.
what about the Flintstone cars?
Well, you should check out Fred's heels.
Yeah.
Now, those brake pads are some serious calluses.
All right, let's jump to another question. And all these questions are from our Patreon listeners, so we're grateful for that. Artist formerly known as James Smith, hello, doctors and lords. Chuck, congrats on your land in Scotland. So there you go. Quick question. Bobsledding is an awesome sport to watch. How many Gs are the bobsledders experiencing at top speed? And also, are there Zambonis for their eyes like in skating?
Oh, that's cool.
Good question.
Cool.
Yes. The answer, let's see. The Zamboni question first. There actually is a lot of grooming of bobsled runs.
Ooh.
I do not know exactly whether they drive a vehicle down.
Can you imagine?
Like a little crawler. I do not know if that's the answer. But they pour water down them. They sculpt them. There are things that are made and changed. The channels are changed. The temperature is controlled. So there is a lot going on that's Zamboni-like on a bobsled run. That's 100% true.
And during the competition, there are like track grooves that are created by the former runs.
Right.
Yeah.
And you have to actually compensate for the track grooves that are already there. The person who is actually pulling the two cords
driver
to
of the
steer
sled.
the
Levers,
driver.
yeah.
Yeah. So
Yeah.
it's
You're
pretty cool.
absolutely right,
Chuck
Chuck.
at the fireplace sipping scotch.
Once again, I'm down to the lodge. I'm just like, you do realize that you didn't account for the track grooves. This is your problem, sir.
Also, I want to add one thing before we take a quick break. The G forces you feel have nothing to do with how fast you're moving.
Ooh.
They have to do with how fast your velocity is changing. So their biggest G forces, Charles, are going to be like when they bank the turn, right?
A G, A G is the acceleration rate of 9.8 meters per second squared. The amount of acceleration you feel when you're
Falling.
in free fall near the surface of the Earth. I did a quick calculation just now in the past 30 seconds in my head. So I'm not sure if it's exactly right. You can't quote me on this. But based on what I think, how fast they're going down the hill, the angles of the turns and the velocities and the banks and so forth, you're probably hitting at least 3 and sometimes 4 times of gravity. So 30 to 40 meters per second squared of acceleration. So 3 or 4 Gs is my top of the head answer. I'd have to go back and do more calculation to make sure that that's off my head.
All right, let's take a quick break. When we come back, more with Charles Liu, our geek in chief, who's breaking down the physics of the Winter Olympics when Star Talk returns. We're back. Star Talk, Cosmic Queries, Sports Edition, the Winter Olympics, all kinds of questions. We're good here. So, who's got the latest one?
All right, here we go. Next up, Kevin the Sommelier. Hello, Chuck, Cubed, and Gary.
a wine
This
guy.
is you're going to love the ending on this one, Neil. This is not so much a science question, but a Seinfeldian observation. Does the luge and the skeleton? Well, we'll see. Does the luge and the skeleton events just seem like a drunk friends dare? Keep drinking up. There, yeah, I told you you'd like that, Kevin the Sommelier.
Yes,
Nice one.
I am certain the luge is for crazy people.
Oh, you can imagine someone up the top of a mountain,
What?
sat next to Chuck with an empty bottle of scotch, says, there's that tray over there, I could beat you to the bottom of the mountain.
On the tray.
How many of wait. Have
Now,
you
wait a minute.
also-
Which one is head first?
Skeleton.
is head first.
That's the
Skeleton's head
skeleton.
first.
Okay.
Yeah.
Luge is feet first.
Okay.
Yeah. I feel like luge is like safer, right? But how many of you have you all gone
Really?
down a hill in a sledding? How many of you have you? 3 of you gone sledding before?
I mean, we have all been children, Charles. Yes.
Yeah. But we've not done it on an ice track.
Right, on an ice track as an adult.
No.
You know,
Oh, no.
or
No
the
chance.
closest I came to that once, I was on an icy hill. Or I was maybe 40 feet
Wait,
tall.
Charles, I
It
gotta
was
interrupt.
fantastic.
Wait, Charles, I gotta
Do you
interrupt.
know how awesome it feels to go
Charles,
down at
I
zillion
learned
miles an
from
hour
Chuck.
on the ice?
I learned
What,
from
what,
Chuck
what?
yesterday. There's common sense and there's black people
Black sense.
Okay.
That's right. There's
Which is
common sense and there's black sense.
Black sense. And so, as an adult, if you're going to say, sit on this tray and go down this icy tube at 199 miles an hour, we're going to just say no. Okay.
Yeah, my answer is, if you tell me to go down a tube head first at 100 plus miles an hour, my answer is, why don't you just shoot me? I'm here. Why am I going to do the work for you? Why am I doing the work for you? You want to kill me? Go ahead and kill me. I'm right. Go ahead, do it. Do it. I'm right here. I'm right here. Go ahead and do it.
Good arm. I don't have the sense, I'm sorry, but I'm really glad in that instance I didn't, because going down that hill, basically ice, on basically a sheet of plastic, at a gazillion miles an hour, was one of the most fun and exhilarating and awesome things going on. And there were other people, many of them kids, but also some adults going by me, some of them faster, some of them slower. Some of them piled up at the end of the hill. It was so much fun.
Charles, you know who gets to say that? The people who didn't die.
Yeah.
There is a survivor bias, I admit.
Okay, Charles, just to tap the brakes, pun intended on this, for Luge and the skeleton, they don't have any.
Yeah.
There's no brakes on the Luge or the skeleton, so there's the chance of an impact, which is my best thought.
Well, we shouldn't understate the danger. Every year, professional lugers are killed. Professional skeletoners and bobsledders are, they die from.
And
not
you know
making
what's
me do
funny?
this.
Wait, I'm so glad you said that, Charles, because it's the only sport where they don't show you when it goes wrong. NASCAR, Formula One. Things go wrong, you see the car disintegrate, break apart, and then you see the guy crawl out of the cage. Even for years, ABC Wide World of Sports had a guy coming off a ski jump, and they called him the agony of defeat. Yeah. You will never see anybody promote what happens when the luge goes wrong.
Yep.
Yeah, because it would be ugly.
Yeah, because the guy shoots out of the tube.
Very, very ugly.
Yeah.
No.
They don't even They don't even follow it with the camera. The guy shoots out of the tube, and then the cameraman goes,
There are some things.
Yeah.
There are some things. All right, let's move on. And
Another
it wouldn't be
orbital
the same.
satellite launched. Okay.
Yeah. Okay. This wouldn't be the same with a Sports Edition grab bag if we didn't have Violetta and Mum Izzy asking a question.
Violetta!
Hey,
Violetta, Mum
okay.
Izzy,
Great to see you.
She has now dubbed herself as Astrophysicid.
Oh, that's
Excellent.
kid. Wow,
Nice.
that's
Good choice.
Yeah.
Good
Okay.
choice.
Is she like 18 by now? Hasn't she been asking questions for like 20 years?
13 and 1/2, Neil.
Okay.
13 and a half. Okay, fine.
Yeah.
All right, the question
I
is
hope
this.
we're not being catfished, and one day we find out that Violetta is like a 43-year-old dude. Hello, Neil. Hello, Charles, Gary.
Yes.
My name is
right.
Violetta, and I have a question.
All right,
What
do
are
you got?
some of the craziest sports, past or present, ever to be included in the Winter Olympics? I can't imagine there was throwing the axe while skating on ice, but that sounds like it should have been back in the day. I will enter one sport in here, the 90-meter ski jump. I am going up a really, really high tower. I am icing down a ski slope and jumping and trying to fly. Now, if that isn't crazy, then I don't know what is.
No, isn't she talking about events that are no longer there? Or just, are we picking crazy events that they've
Past
got now?
or present? Past or present, Neil? Was
Right.
the,
So, Charles, are there defunct sports in the Winter Olympics as there are in the Summer Olympics? Like they don't have the
must
tug of
say yes.
war anymore, or the rope climb.
After, we did this kind of question for the Summer Olympics in
Yeah.
a previous episode. After that, I went and took a look at the previous sports because I just found it so fascinating. And here is the one that I found for Winter Olympics, which I think is the wildest and most interesting one.
Ooh.
It's called Mountain Military Patrol.
Really?
In the 1924
All right.
Winter Olympic Games, there was a sport called Military Patrol, where 4 military officers, 1 officer, 1 non-commissioned, and 2 privates, carrying backpacks totaling at least 50 pounds, and carrying rifles, except for the officer who carried a
course.
pistol. The officer carries a pistol.
And no backpack.
They had
No
to.
backpack.
Yeah, right.
And he's got a snowmobile. But other than that,
The 4 of them together had to climb at least 3,000 feet in elevation on cross-country skis going at least 15 miles. And then once they got there, shoot. and do target practice.
Okay, that sounds to me just like a way that America found to invade another country.
But this is French, and this is Swiss.
Oh, these are the Swiss.
This is European.
Oh, so
Yeah,
this would have
Winter
involved.
Olympics.
So this would have involved the officers sitting at a table while the privates practiced their shooting, and he drank cognac and while eating brie.
I couldn't tell you, but apparently this was a sport.
Was
And
that,
these
a one,
teams-
was that a one-time appearance, or did they?
It showed up again as a demonstration sport several times later, but it has been discontinued since about 48 was the last time it was a demonstration. But imagine that, a sport where you have a team of military officers skiing and then climbing and then shooting at various times, we're all carrying heavy backpacks. That is a sport.
So that became the cross-country pentathlon, I guess. What's the one where they
That's
cross-country?
Biathlon today,
biathlon.
right?
Oh, the
And that's
biathlon.
evolved to a biathlon where you ski, shoot, ski, shoot, ski, shoot. But nowadays, those rifles are very light caliber. They're heavy, yes, but much less heavy than a true machine gun or a weapon that actually a military person used to use. And now that it's really a streamlined sport that combines the skill of shooting, target shooting, not actually military shooting.
Charles, you sound like,
swimming.
the grandpa on the
through
porch.
the water.
Back in my day, the rifles were heavier, and we had to climb uphill both ways and then shoot. Now,
Yeah, maybe. I'll
we
say this.
shot at each other.
I
You
have
should
been
see how many bullet holes I have right now from the Olympics.
I have been very fortunate in my life, never have to fire any kind of weapon in anger, and so I cannot speak for what is easier or more difficult.
All right,
But
what
I
a
can give you the
qualifier,
numbers.
Charles. What a qualifier.
I know, right,
In
right.
anger. I shot the guy after I calmed down.
Don't dredge up that
was
memory.
I don't even want to probe that qualifier. Chuck. let that one go.
All right, do we have time for another one? Hopefully.
Yeah, Stuart. Yeah,
Charles
make another
Macco.
one.
Hello's Dr. Tyson and Lou. What impact, Chuck and I, we're not here. What impacts will climate change have on Winter Olympics throughout the rest of the century? Of course, some sports are already played indoors like skating and curling, but might we see an end to sports that require outdoor cold temperatures?
You'll see an end to them in different parts of the world where they traditionally existed. Remember, with global warming, like 100 million atomic bombs worth of extra energy floating around in the atmosphere at any given time, right, for every degree change in Celsius. There's going to be a lot of motion. So some parts that were traditionally cold will get warm, and some parts that are traditionally warm will get colder, right? So in Switzerland, for example, or in parts of France, the famous ski areas, Chamonix, places like that, they're already having real trouble getting enough snow to have a decent recreational ski season. So their sports seasons have been severely curtailed already, and that's true. Other places where currently nobody goes to, though, maybe certain areas of mountaintops, certain places where polar vortices coming out from different parts of the Arctic will create new flows of cold. Those areas might get much more snow and much more ice than they do today.
Yeah, but
And then
no one has
those
put a
areas-
ski slope there yet, so that this
Right.
would
So
change
it
the
will
business
change-
landscape.
The entire landscape will change. You're going to have a world where the sports will still continue, but they'll be in completely different places. Places where there are no ski slopes or winter resorts today, they will be there. And in other places where there were for decades, maybe even centuries, those places will struggle. That's what's gonna
Welcome to
happen.
the 2050 Olympics of Winter here in Fiji. So,
It's going to be weird. It's going to be strange. We all have to adapt.
I mean,
Gary, give me another one.
by this time the show goes out, we'll have done our ice and snow show, and we have a great guest, Dr. Peter Veals, who makes artificial snow. So maybe he is the vanguard of a boom industry making powder snow.
There it
We
is.
shall see. Right, one more question.
Slip in one more, Gary. See if we can get it.
All right, Anna C. Hickman. Hello all. I have a question about Paralympic athletes and a future time somewhere when I am probably already dead. As a wheelchair user, I am an avid follower and participant in adaptive sports, and I know sometimes there is chatter about how an adaptive athlete has some advantage because they use specialized equipment when compared to regular athletes. If we as a human race got to the point where we had outposts in space, and there was interplanetary Olympics, would an athlete who already knows how to navigate in a compromised body when compared to able-bodied athletes have an advantage in competition? Would the roles potentially be reversed and the power athlete be the one with the perceived advantage?
I would totally see that as a real possibility.
Yeah, I mean,
without
as would
question.
I. Yeah,
Without question.
I think what we declare to be an advantage or not, it's according to some norm that someone establishes. But you can imagine constructing sports where whoever was previously advantaged now becomes disadvantaged. I mean, you can come up. I mean, look at how random sports are anyway. Take this ball and put it in a hole or in a hoop or jump or crawl or
curling.
Curling. So I welcome your follow up on this, Charles. But it seems to me that we've created a world where para athletes are trying to do what non-para athletes, what has been invented and styled for para athletes. Imagine a whole set of competitions designed specifically for para athletes, and then they have the advantage, right? So a new world, like you say, if you go into space, you go into zero G or low G, all the dynamics changes about who's good and who's not good at some sport. So that's a fascinating new world. I think it's underexplored in people's creative ways.
Yeah. I have very little to add to that, Neil. I think you're 100% right. And just our understanding of what is able-bodied and what is a compromised body varies with every environment that we go into. New sports are invented all the time. A lot of times we forget. Right, we were just talking about military patrol, which is no longer being done anymore. But that was a real sport in the 1920s, right?
Or an advertisement for officers' training school.
You don't have to carry the rifle, right? We should always be adapting to new places and always looking at human beings as whole individuals. And when we see what an environment provides for sport and recreation, we should leap on it and find it and use it and make it our own, regardless of who's out there, and turn it into fun. That's what the Olympics should be in the end, right? Fun.
And the only difference is, going back to what Neil said about the fact that para athletes have to do what able-bodied athletes do. If it were the other way around, take the able-bodied athlete and make them compete in the same Paralympics, they lose every event. Like the gentleman that we had on that shoots, who is the archer, who does it with his feet. Let any archer try to do that, and they lose.
Right. Yeah, Matt Stutzman was the guy. Right.
That's it, Matt Stutzman.
Well remembered, Neil. Yes.
One of my favorite episodes. All right, Charles Luge, fellow astrophysicist, geek in chief, and wherever I am on the geek spectrum, he is beyond that.
You are too kind, sir.
All right.
Only on this show is that a compliment.
There you go.
All right, Chuck. All right, Gary.
All right, thank you.
This has
It's a
been
pleasure.
Star Talk Sports Edition, Cosmic Queries Grab Bag, all about winter sports. Neil deGrasse Tyson here. Keep looking up. This is Star Talk, a Things You Thought You Knew edition. Chuck, is that your favorite format?
It's probably explainers are my favorite, but things you thought you knew is my second favorite because I am aware, thanks to working with you for almost 12 years, that I don't know jack crap.
No.
That is what I have learned.
Well, so
in
things you
all
thought-
this time we have spent together is that I used to think, I thought at one point I knew something. I thought I knew something. And then the universe sent a man named Neil deGrasse Tyson into my life. And then the universe said, boy, you don't know.
You don't know shit about anything. No.
You don't know nothing, dude.
Okay, so things you thought you knew is like a superset of explainers. So first one is going to be rainbows.
Okay, that sounds
Nobody
delightful.
doesn't love rainbows.
That's
okay?
right. Sounds delightful. I love it.
Okay, nobody doesn't love rainbows. Okay, I have a quick rainbow story. Ready? I knew a couple. They were dating, and the guy was a little high strung, and she was sort of like normal, right? And she pointed. We were driving. I happened to be in the car with them, and there was a beautiful rainbow out the window, and the guy was speaking about something else, and I said, "Oh, look at the rainbow," and she said, "Oh, that's a beautiful rainbow," and he says, "No, shut up! I'm talking about something else," and I said, "What? Who doesn't like rainbows?" And she turned to him, and 2 months later they broke up. So,
Yeah.
I don't know.
Well, he didn't know it, but they were already broken up.
Chuck has seen some therapists. He knows the signs.
That's it, buddy. Let me tell you. So
All right,
what's number 2?
Second segment just going to be about zero.
All right.
The number zero.
The number 0.
Yeah, zero's a number. Just get over it. Right.
Okay, yeah. You never think of 0 as a number.
Yeah, but it is. And we need it, it turns out, for most of what we do in mathematics. So there's that. And the third one is, what do Zoom calls and Einstein's theory of relativity have in common?
All right, you've gone too far, Neil.
I know. Have I stepped off the ledge?
You just, seriously, bro. You are over the cliff.
Oh,
That's it.
Give it a chance, Chuck.
Oh, my God.
Let me try.
I don't know how you going to pull that rabbit out your hat.
Okay. All right. Let's get to our first one in this first segment. So, Chuck, we're going to talk about rainbows.
My 8-year-old daughter loves rainbows.
Okay. Well, make sure she listens to this. All right. So
That's cool. Yeah.
So it was not until Isaac Newton, my man.
That's your
man,
boy.
Okay. Early 1700s. He wrote a book in 1704. It was just called Optics. One of the rare books that he actually wrote in English. All his other books were in Latin, which was the
Well, he really was a nerd.
Okay. But in there, he figured something out.
Okay.
Everyone, of course, had known about the colors of the rainbow: red, orange, yellow, green, blue, violet. Okay. And people have seen, chandelier, light will come through the chandelier and you'd see rainbow colors come out one side or another. Everybody until Newton presumed that those colors were somehow getting generated inside the chandelier glass.
Okay.
Or inside the raindrop.
Right.
That it was some property of the medium itself. Nobody was thinking that pure white light is composed of those colors.
Oh, if only we could learn that lesson in our society.
Ah,
God,
Chuck getting all sociological. Chuck getting all. So imagine if Martin Luther King were more physics fluent. That would have been a whole different "I Have a Dream" speech.
It would. I have a dream that one day we will recognize the white, black, red, or brown. We're all white. It's okay. It's okay.
Everybody would have tipped their head and said, "What?
It's what?
We invited this man
get there with you. I may not get there with you, but we'll all be white one day."
Stop.
Okay.
So here's how he did it. Okay, so he puts white light through a prism. Okay, and out the other side comes the colors of the rainbow, much as what we all remember from Pink Floyd's Dark Side of the Moon album cover.
One of the best ever.
All right. So he then, and this is what makes Newton, he said, let me take another prism and put it upside down next to it.
Ooh.
Okay. And this would kind of reverse what had just happened. And when he did that, out the second prism came white light.
Okay, how did I not hear? And all the time we've been working together, this is the first time I've ever heard this story.
Yes.
this is brilliant.
Yes!
Because in doing so, he proves that it has nothing to do with the actual medium itself, that the light coming in was merely separated, and then by coming out and going back into another medium, it combines. It's the light. It's just the light.
That's why he is Isaac Newton and the rest of us aren't. It's that simple.
That is brilliant.
And it's simple and brilliant.
Yes, yeah, exactly.
That's what makes it extra brilliant, is how simple it is. So at that point, it's easy to sort of extrapolate that a rainbow is just sunlight broken up into those same colors that the prism did for you.
Right.
Okay. So now, what's going on inside a raindrop? So sunlight enters the raindrop at a particular angle. All right. Actually, it comes in at all angles, but only one of those angles will internally reflect off the boundary between the raindrop and the air. Okay, this is one of the most fascinating features of optics.
Okay.
So in other words, if I'm underwater and let's say, have a laser, so we get a nice sharp point, and I point it upwards, not straight up, but at an angle, at a slight angle. When that laser beam exits into the air, it bends. Okay? It's bent.
Right.
It's bent. Okay, you can picture this. You can try it yourself if you have a pocket laser. Okay. So it's easy then to expect that a similar thing is happening between sunlight and raindrops that was happening between your sunlight and your prism. So, but the fun part is the sunlight goes inside the raindrop and bounces around a couple of times before it exits again. And by the time it exits, all of those colors have been separated out from the white light. And thus you have this participatory rainbow where all of these droplets of water participate in one coherent rainbow. Now, the angle the light exits creates a rainbow that you see. Okay?
Right. Okay.
Right? You only see what enters your eye. You can't see what doesn't enter your eye. Correct?
Right.
That makes sense.
Right. Makes sense.
By the way, that itself was a discovery from 1,000 years ago. Ibn al-Haytham was a Muslim scientist back in the golden age of Islam. He was the first to deduce that sight is not you beaming stuff out of your eyes. It's completely passive. Your eyeballs are just sitting there waiting for light to enter and for your brain to then make an image. This is profound because before then you had these legends like Medusa. Yeah. All right. How does Medusa work? How does that work?
Well, when you look her in the eyes, she turns you to stone, basically.
She turns you into stone.
Because she's casting whatever from her eyes.
From her eyes, correct.
That's what
you could only think that if you have no idea how vision works.
Right. Or if you're creating X-Men, but that's a different story.
Oh, he's got his little visor thing that can send out the beams. So what that means is all of the rainbow light that's coming to you is exiting those raindrops at the precise angle that enters your eyeballs. Okay? Okay. That means your rainbow is unique to you.
Wow.
If I stand to your left or right or above, doesn't matter. If I stand somewhere else and we're looking at, quote, the same rainbow we tell ourselves, we're not. You know what this fact means?
I do not.
Okay. Every rainbow you have ever seen has been exactly face on to you.
Aha. And so every rainbow actually was made just for me.
Just for you. You have never witnessed a rainbow at an angle.
Right.
So think about that, because if your rainbow was a real thing in the sky, I could move to another location and look at it from a different angle.
Right.
If it was an actual thing,
Like
that was
anything
there.
else, right? Like a mountain, a tree, or
A
whatever.
mountain like anything else. Okay.
Right.
So, if you wanted to go to the base of the rainbow, you can't. Because that would be taking a different angle of view on a thing that does not really exist as a physical entity.
And now you have just explained how I have wasted a significant portion of my life trying to find that pot of gold.
If you're going to hide a pot of gold, put it at the bottom of a rainbow. Nobody will ever find it.
Exactly.
Ever. Yeah. So just a little known fact. Now, the light that's inside the raindrop, this is like inside baseball here. You ready for this? This is
Go ahead.
This is rainbow 201, not 101. So the light inside the raindrop sends out not only one rainbow, but multiple rainbows, but each next one is a little weaker than the previous one.
Okay.
And because the second rainbow that comes out had an extra reflection to it, if you ever see a double rainbow,
it means that you're tripping on mushrooms.
What's that?
It means you're tripping on mushrooms.
No, if you see a second rainbow. No, Chuck,
Double
it's just
rainbow.
physics. No, yeah, sometimes it's actually just physics, not the mushrooms you've been consuming.
Okay, got you.
So,
but go ahead. The double
with
rainbow.
That, two properties of that second rainbow is, one, it's much dimmer than the first.
Got you.
It's always there, but generally it's very hard to detect because it's so dim. So it's much dimmer, and the sequence of colors is reversed.
Oh, no.
From the original.
That is, first of all, that's dope. Secondly, who knew? So the double rainbow is kind of like the reverse rainbow.
It's an inverted rainbow to the first rainbow, and it's dimmer. There's actually a third and fourth and fifth. They're called the orders of the rainbow: first order, second order, third order. But they're so dim, and if the sky is bright, you just will never see them. And there's a famous YouTube video some years back. I think they just call it the double rainbow guy. He's hiking.
Yeah, that's
in the
what I'm
mountains.
saying. He's tripping on mushrooms. That guy.
And he sees two rainbows, and he falls prostrate to the ground. And said, there is a God, and it's
double
so
rainbow.
Beautiful.
It's
double
so
rainbow.
Beautiful.
And that's how you behave if you don't know physics, right? You just think it's just physics, really.
That's all it is. It's just physics. Yeah. Once again, Neil, way to ruin rainbows.
No, I'm just saying. I want you to reserve your sense of wonder for things for which we still do not understand. And not apply it for things that are completely understood. There will always be a moving frontier of science. Where our area of knowledge grows, so too does the perimeter of our ignorance, leaving us with no end of this universe to stand in wonder as we gaze.
Wow. Okay. Thank you, people. That's the show. Ain't nothing left to say. Nothing left to say. That's it.
Explainer video. There you go. All about rainbows. So, Chuck, we got to take a break. When we come back, we'll do a little bit more of this. We'll find some other subject, if you're game.
Sounds great.
Let's do it. Okay, Star Talk. Stuff you thought you knew. We'll continue. We're back, Chuck.
Yes.
Things you thought you knew. You ready for another one?
I'm ready. Let's do it.
Let's go there. And by the way, I picked these based on how familiar we think we are about the subject, and then throw in some things that you never knew.
See, that's the cool thing, though, because, I mean, if we were just going to talk about, like, gravitational waves, of course we don't know none, you know what I mean? Like, who's an astrophysicist? There's, like, what, 20 of you? You know what I mean? There's, like 7 of you sitting around,
So this is not just, let me explain stuff that you can get on a wiki page. It's like, cool, fun stuff you never thought.
No, it's the twist. The twist that gets you, man. Okay. Like the inverted rainbow. Who knew that? The orders of rainbow. Who knew that?
Yeah.
Like, I mean, that's stuff that you honestly, but everybody knows rainbows.
So
anyway.
For this segment, we're going to talk about zero.
All right, here we go again. Okay, now I'm gonna be honest. This is gonna be tough for you, man. Come on, seriously.
Are you ready?
All right, here we go. Zero.
Okay. All right, so let's do this. So zero is a number, but it wasn't always a number. In fact, no one ever imagined it could be a number. In fact, no one even imagined how to imagine it.
Okay.
Why would you?
Right.
What were numbers for?
Right. Who counts nothing?
Right. Numbers are for counting.
Right.
Okay, how many chickens do you have? 3. How many cattle do you have? You count things. So nobody had any use to count zero. It just was not there. For most of civilization, this was the case.
Right.
Even through the Roman Empire.
Wow.
We think of them as highly civilized, whole
Yes.
cities and
Right.
hot baths and armies, and if that's equivalent to
Aqueducts
civilization.
and
aqueducts, right?
And they're so sophisticated, their numbers were letters.
So, Roman Empire, they can count. They used Roman numerals, right? We learn Roman numerals in elementary school, don't we? Still,
Yep.
I think, right? And the reason why we learn Roman numerals is so that we know how to count Super Bowl games.
That is kind of the only application
No,
left,
one more,
right?
one other for some movie sequels.
True.
That's it.
True.
That's it. I don't know any other application.
Okay. Yeah.
Oh, I know. Also, lowercase Roman numerals are the page numbers in books before you get to the actual chapters of the book.
Okay. Yeah, that's true.
Look at the bottom of the pages. Those are usually Roman numerals. And then they restart from one at the beginning of the
page
book.
one.
Okay.
Yeah.
So I don't know if you've ever thought about this, Chuck.
Uh-huh.
You can't write zero with Roman numerals.
No, you can't. Right.
There is no symbol for zero. It's not because they didn't come up with it. It's that the concept of zero was not yet invented.
Wow.
So when they made the Julian calendar, that's the one that has a leap day every 4 years. And because they knew enough to know that the calendar needed it, that calendar, the Julian calendar, which anchored its starter date on the birth of Jesus. Okay, so this obviously came later after Constantine. I think Constantine brought Christianity to the Roman Empire. So in the Julian calendar, they went from 1 BC, BC of course stands for before Christ, to AD 1. And AD is in Latin, Anno Domini, the year of our Lord, 1. And there was no year 0 in that transition. So when would Jesus have been born? All right. And, in the mythical year between the two, he can't be born in AD 1 because that's after, and he can't be born in BC because that's before. So this was an issue.
Oh, I got the answer.
What?
It's a miracle.
Okay, that's a good answer, Chuck. Well, later biblical research would show that Jesus was probably born closer to 3 or 4 BC, and so, but the calendar was already in place, so you're stuck with that. There's a mismatch there, 3 or 4 year mismatch.
Yeah, we got to play this hand. We got to play this hand, bro.
We've got to play it. Okay, so now move time forward. Going, it's in the 600s, 700s, I forgot exactly when, in India. There were great advances in mathematics there, where they even developed the numerals, early versions of the numerals we now use.
Okay.
Rather than Roman numerals. Okay.
Right.
Roman numerals were letters. These are now sort of symbolic shapes that would then represent the numbers. And in this effort was the hint that maybe you might want a 0 in there. Okay?
Okay.
So we're crawling now before we can walk, but the seeds are planted. These new mathematics work their way to the Middle East. Okay? And Baghdad specifically, a big trading post from all corners of Europe and Asia and Africa. And there it was. Ideas were put across the table. This is the golden age of Islam. All right,
Wow.
major advances were made in engineering and astronomy and biology, physiology, and vision. That's where the discovery that in vision is a passive phenomenon, not active. And so all of this is going on, and then the zero was perfected.
Oh,
The zero is perfected. They call those numerals Hindu numerals.
okay.
But we today call those numerals Arabic numerals.
Right. Yeah.
Okay? So this is the full tracking there, because in the Middle East, an entire algebra rose up, and arithmetic and algebra rose up, invoking zero, and you have negative numbers, and so mathematics is off to the races. Algebra is one of very common words in English that has its roots in Arabic. A lot of the AL words, AL is the in Arabic,
Yeah.
as I
Al
understand
Green.
it.
Yeah.
Yeah. So algebra, algorithm,
Right.
another one, alcohol. These are all traceable to that period. But all I'm trying to say,
The
Chuck,
best
is
of which is alcohol.
alcohol. Good going, guys.
There you go. Way to do it.
So I'm just saying zero. Just consider how late zero came in civilization. The Egyptians knew nothing of zero.
Right.
But it's there, and we've got it. And so now,
So what is this? What is this I hear about the Mayans and zero, that they somehow had something to do?
I don't fully know my Mayan history, other than that their calendar was they really worshipped Venus in the sky.
Oh.
And so the calendar was sort of Venus based. The calendar in ancient Egypt was based on the star Sirius. I'm talking about the New Year, when you start the New Year.
yeah.
'Cause that's completely arbitrary when you say the New Year just began. Completely arbitrary. Just pick a date, and whatever matters in your culture, call it the beginning of the year. It's not, and to this day, when is the Chinese New Year? It's in like late January, February, right?
Right.
Everybody's got a different starter date. And so that
The Jewish New Year is another New Year that,
Yeah, everybody's got their New Year.
everybody's got their own New Year.
The academic calendar has a New Year. It's September 1st, even though they don't say it. It really is that. All the academic folks come back from summer vacation. Children buy their school supplies. That's, in a way, a New Year's Day for school, if you want to
Gotcha.
think about it.
All right.
That's
All
how
right.
And by the way, one quick thing. You got $100 in your bank account, and you go withdraw $100 from the cash machine, and the bank tells you what?
Don't do this again, man, because by the way, you think you have $100 and you don't. See,
Okay.
what you
here's the fun
forgot
part.
was the electric bill came through yesterday.
Before you withdrew the 100.
Before you withdrew this $100.
You sound like this has happened to you, Chuck. All right. So here's the thing. You have no money left in the bank, and that's bad. But what's worse is to have negative money
Yes.
in the bank. And so this whole concept of negative numbers arose and made complete sense once you pass through zero, and now instead of something coming your way, you now owe it.
Right.
And so the mathematics began to mirror commerce and the needs of civilization as we move forward, because we're doing much more than just counting things.
So this is like the birth of modern accounting. Once you find zero, that's when you're able to actually have, a ledger sheet that shows you minus and pluses and all that kind of stuff.
Yeah, it's one of the few places in the world where it's really good to be in the black. Culturally. Apparently, no other way is it good to be in the black except on the accounting sheet.
Oh, that's great.
So now you can go into negatives, and this keeps going with math, and you find other needs of culture and civilization and science where whole other branches of math have to be developed. And so this just went on, and then we got trigonometry, all the stuff that you thought the teacher was just being angry with you, giving you these assignments. These are entire branches of math. The zero started it all, where it gives you deeper insights into the operations of nature.
Absolutely. Wow. That's pretty cool. I mean, all this just from nothing.
Yeah, from
all,
nothing.
all this came from nothing.
And so in this way, nothing means something.
Right.
And what's that song from the 80s?
Nothing from nothing leaves nothing. You gotta have something if you won't be with me.
Nothing from nothing leaves nothing.
Leaves nothing.
I think that's a legit equation. I have to think about that. 0 minus 0. You just can't start dividing, right?
By 0.
Because then you end up dividing by 0, and that's illegal.
Right. You've broken a law of the universe or something. But you divide
You do that too
by
many
0.
times,
Right.
Beetlejuice shows up and it implodes.
Exactly.
Right? So, Chuck, I just want to bring you up to speed on 0. That's all.
Yeah. I got to tell you, I've never been more impressed with nothing. So this is cool. This is very cool.
So, Chuck, we got to take a quick break, but when we come back, we can slip in another stuff you thought you knew.
Awesome.
Are you game?
I'm totally game.
Let's be totally game. All right, we'll be right back. Chuck, we're back.
Yes.
Yeah,
What
I
do we
another
got?
topic for you.
All right.
What do Zoom calls and Einstein's theory of relativity have in common?
No one knows how either of them actually work.
That's a good answer.
I'm going to say that's got to be the answer.
That's a good answer. So here you go. You ready?
Okay, let's do it.
What we affirmed in Einstein's theories of relativity is that space cannot be thought of just as space. Time is a fundamental coordinate right alongside space. Right. So that when you ever want to think about events, phenomena, past, present, future, you have to think of space-time. You can't just think of space or time as separate things. And there's an entire set of equations that fold the two together.
That's the first part I am so cool with. I literally get it, But when you talk about proving it mathematically, I'm still just
that's how you know it's going to be tight. That's all.
Yeah,
that's
of course, because
it
keeps moving, it keeps working. When the math works, it works. Yeah, that's
works,
cool.
Right?
Man.
Okay, so let us, for those who might still be uncomfortable with the space-time concept, what you don't know perhaps is that you live that way. Mm-hmm. There's no other way you live. It's so intuitive, you think it's complicated, but it's easy. So if I say to you, Chuck, you ready? Okay.
Yep.
I'd say, Chuck, let's have lunch tomorrow at noon.
I would say, oh my God, as long as you're paying, that is such a wonderful offer.
Okay. Chuck, it's on me. Let's have lunch tomorrow at noon. What is your next comment back to me?
Where do you want to eat? Where do you want to eat?
Because the time alone was insufficient for your life and my life to intersect. Time is alone will not make that happen. You also have to give a spatial coordinate. Right. Is it the diner on the corner of, Hollywood and Vine at 12 noon? So you have a space coordinate and time coordinate so that we can both meet.
Right.
Okay? By the way,
leave it to you to give me a coordinate where I can't get to.
wait. So watch. If you go to the diner at the corner of Hollywood and Vine,
right,
yesterday, and I go there tomorrow, we were in the same place.
We were,
but not at the same time.
Okay,
doesn't work. Okay. Let's keep going. You were at the diner yesterday, and I'm at the diner tomorrow. We're both in the same place, but not at the same time.
Right.
Okay.
Which is what I call Neil's favorite lunch. Chuck, yeah, you were here yesterday. Good.
Okay, so now watch. So now you're at the diner in the corner, and I'm at, this works with Starbucks. You're in that Starbucks. I'm in a different Starbucks.
Okay.
We're at the same time, but not at the same place.
Right.
Yes, it's the same brand, but it's a different location.
Yeah, but it's a different location, yeah.
Okay, so you need to be at the same place and at the same time for anything to happen where you have two things that want to coordinate together.
Right, okay.
Okay? All right. So how does this manifest? Let's go in the universe, and there's an asteroid headed towards Earth. You could do the Bruce Willis thing and what?
Blow it up.
Blow it out of the sky, which takes a lot of wasted energy. Or you can deflect it. Well, how do you deflect an asteroid?
Movie. Not a good movie.
How do you deflect an asteroid? So here it is. If you left it alone, it will collide with Earth, which means it will be in the same place at the same time that Earth is sometime in the future, at some point in the future. Okay? So what I can do is I can speed up the asteroid.
Ooh, I love that.
You speed it up, then it gets to that location in my orbit before I do.
Exactly.
So it's at this, we exist at the same time, but we're not in the same place.
That's a whole nother way to look at deflecting an asteroid.
That's what's going on when you deflect an asteroid.
That's awesome.
Or you could slow it down. Then we get to that point before it does. We keep moving and it goes right on by behind us.
Oh, man, it's the proverbial mental exercise that everyone does when they have a car accident. If only I hadn't forgotten my keys. If only I had left a little bit earlier. I would have never
been in that spot at that time for the drunk driver. Correct.
Right. Yeah.
It's a mental calculation you do. Right. And it works in simple ways that we don't even talk about, but it's so simple. You cross the street, 5 minutes later, a bus drives down the street. You didn't say, "Oh my gosh, I was almost hit." No, you
Oh, you're a bit of a drama queen. You know that, right? My God, I was almost hit by a bus. Did you see that? What? No, it came by here 5 minminutes ago. It was just barreling down the street.
It was in the same spot I was
right there. I could have died.
Right, you would not have died. And by the way, in relativity, we call these world lines. Your world line is where you are in space and time, which is always in motion.
Right.
Because time, even if you're sitting there on your butt, you're moving forward in time.
Right.
By the way, this affects time machines. All right? If I give you a time machine and you say, okay, you want to go into the future. How far do you want to go in the future?
Oh, I'm going to go at least 200 years just to see if we're still here.
Okay, but suppose you say, all right, I don't want to land in the winter. Let me land in the summer. So I want to go 200 years and 6 months. Okay. Let's say, because we're recording this, it's cold outside right now.
Right.
So you do that. All right. So we'll go in your time machine, go 200 years, and then you walk out of the time machine. You will suffocate in the vacuum of space. Because Earth is not just
spinning, it's moving while it's spinning.
Okay, so you will land in the same spot that Earth was in its orbit, which is a different place than where it is 6 months from now.
Oh, man.
Which tells you a time machine can only work if it's a space-time machine.
That's right. That's pretty awesome.
You want to move to a location in time and a location in
space.
Correct.
Right.
All right. So.
Oh, wow. That is really cool because.
Okay. So now watch. Watch how this plays out. Right. Are we on the same page now? I don't want to move forward until I hear, Neil, I'm with you.
I am riding this wave with you, buddy.
Okay. So, under normal circumstances, I'm in my office 3 or 4 days a week. I travel a lot. There are seminars and colloquia. Scientists come through the department and they give talks. Mm-hmm. You know, if I'm around, I'm going to attend those talks because they're good. They learn about the latest breaking discoveries made by my colleagues.
Okay.
So we have maybe 3 or 4 talks a week in our division at the American Museum of Natural History. I used to make maybe one of those a week.
All righty.
However, during COVID, I was making 4 out of 4 talks a week.
Okay.
Why? Because Zoom calls broke the space-time alliance. So that now you only have to be at the same time. And you do not have to be at the same place.
Interesting.
As a result, world lines can split and only conjoin on the time coordinate, rendering the space coordinate irrelevant.
But
That is why probably more people attending more conferences, seeing more meetings than ever before. You can no longer use an excuse. Oh, I'm on a business trip. I can't come in. Zoom in. We have you on the Zoom call.
I know. It's an electronic leash is what it is for most people.
And that's how, Chuck, you spent how many months you were filming Brain Games for National Geographic. You're their new host in their new season, yet you didn't lose a bit of the schedule. Your background was different because you were recording with us via Zoom from your hotel rooms and other setups.
That's right.
And so you were still participating because your world line didn't need the space coordinate.
That's true.
And so this is the relationship between Zoom calls and Einstein's theory of relativity.
That's pretty wild. And in a way, I have a new respect for Zoom now.
For breaking the space-time continuum?
Yes, exactly. It's like, who knew Zoom was so damn sci-fi? No, that's pretty. It is. Yeah, I love it.
No, in all fairness to prior means of communicating that predates Zoom, the telephone was kind of like that.
Yeah.
All right. And by the way, do you know what the word caller meant before there was a telephone? It was a visitor to your front door.
I was going to say a handsome gentleman, perhaps.
Yes, you have a gentleman caller at the front door.
Oh, I do believe you have a gentleman caller.
Yes, exactly. That's the meaning of that, with the original meaning of that word. And then Alexander Bell invents a telephone. And so what word are you going to use when you show up at the front door of the telephone line? It's a caller.
It's a caller.
And now we've been that way for 130 years or whatever. So 150 years now. So 1876 was the demonstration of the patent for the first telephone. And so that put people together in time without having to be together in space.
Wow.
So this is one of the great achievements and advances in modern civilization. And Zoom just did it full up with voice and sound and audio quality and saved files and everything.
It's really funny because the video call was purported to be the thing that would change everything in society.
I remember seeing a video phone in 1964 World's Fair in New York.
Wow.
You're like, wow, that's the future. And then you realize you call someone at 6 a.m, they don't want you looking at their...
Yeah, exactly.
The people don't always want you looking at them anytime you happen to call them.
What is that on your face? Don't look at my face. Let's just have the call. Stop looking at my face.
So now you can pre-schedule Zoom calls, and now you can get all dolled up and look all purdy. You can look Zoom purdy.
Yeah, you got to. That's pretty. That's great, though. I mean, it's. Who knew that you could link this back to Einstein? I said you had a tough one, but you did it. You linked it back to Einstein somehow.
And now with asteroids, we're just changing his world line.
Yeah, which, by the way, that is the coolest thing ever. The fact that, I mean, and the idea is you don't even have to knock it off course. You can just speed it up or slow it down. That's because you always think of deflection as a change in
going sideways
in the vector, right? You're going
a vector is direction and speed. Technically, a vector has both of those components. So if you change its direction or you change its speed, you have changed its velocity. The velocity is the combination of those two. So it's exactly right.
But that's great. It's like that. I mean, I am less scared of asteroids now.
No, still be scared. That was not the point of this explanation.
Oh, okay.
No, by the way, a velocity vector is motion that has direction and speed as part of it, like the asteroid, right?
Right.
So you can change its direction or change its speed, or both. Either of those are changing the velocity of the asteroid. Okay, so now watch. You can do that. So with a car, there are 3 ways to change its velocity.
Right. You can slow it down, you can speed it up, and you can hit a wall or another car.
Ideally not.
Okay.
You can slow down. That reduces its speed. You can accelerate, increase its speed, or you can change direction.
Okay.
All three of those can help you avoid an accident.
Right.
It's not just how good your brakes are. Do you have a place to steer so that your world line does not fully intersect with the one that would cause the accident?
You know what? As a person who rides a motorcycle, you just explained how you stay alive on a bike. Those are the three things that are your friend that they teach you all the time. The first is acceleration. Get up and get out of the way. The second is being able to brake properly. But now motorcycles have anti-lock brakes, so that used to be a big deal, not so much. But the most important is being able to maneuver. Yes. So to be able to.
And motorcycles are particularly nimble in that regard.
Exactly.
Right.
Yeah.
Right.
Super cool.
So Chuck, we got to bring this to a close. This was stuff you thought you knew.
Yeah. And now I do.
And the inventory was rainbows, zero, and Zoom calls and relativity. There it is.
Well, yeah.
That's as motley a crew as you'll find.
I was going to say strange bedfellows, but hey, it worked.
All right, Chuck, we're going to land this plane, and I'm going to get out, and so are you. Neil deGrasse Tyson here, your personal astrophysicist. Wait a minute. Wait. Before I end, I did say it, didn't I? Chuck, your show premiered with National Geographic, Brain
Yes,
Games.
sir. Thank you.
The new host. Oh, my gosh.
Yes. Well, please watch it, people.
I'm going to find it. Don't sound that desperate, Chuck.
Oh yeah, that's right. That's not the way. You're not supposed to promote a show by going, "Hey man, please watch it. I got kids." That's not the way you're supposed.
I got hungry kids.
Yeah, hey man, these kids eat so much. Please watch my show.
No, Brain Games. It's a new season, 20 episodes, just dropped on National Geographic. You can get it through the Disney portal.
That's correct.
And check out our very own Chuck Nice. We take ownership of you, Chuck. We feel like you're ours.
That's right. Yeah. Well, that's what I feel that way too.
Okay.
Thank you. Yeah. Thanks, Neil.
All right. This has been Star Talk. Neil deGrasse Tyson here, as always. Keep looking up.